Let's look at the U-sub for definite integrals. This result is extremely fascinating, as you can notice that the change in the x values here is going to be represented as u values over here. In other words, if you had a domain with x values, we're going to be able to convert them to a domain with u values. The procedure is very similar to indefinite integrals. We just have to add a couple of steps and then apply the fundamental theorem of calculus. Let's begin. I recommend that you pick your u-sub to be a function living inside another function. So in this case, I'm going to pick u of x to be sine of x. Then proceed to write your differentials. Now this function notation for u is rather handy because now we could find u sub 1. What does u sub 1 look like? Is basically the function evaluated at 0. And then u sub 2 is the function evaluated at pi over 2. Now we're ready to do our complete U-substitution. We're going to have a definite integral with the domain from 0 to 1. And now we have 4 to the u times du, which we know how to integrate. Now we could apply the fundamental theorem of calculus. We'll simply subtract the two accumulation numbers, and that number is simply 3. And you're done. So u sub for a definite integral requires you to change the domain values into u's. Let's see another example just to bring clarity to this u substitution. This time I'm going to pick u of x to be x squared plus 1. Write our equation of differentials. And now we need to find our u sub 1, which is the function evaluated at -4. And then we need to find u sub 2, which is our function evaluated at 4. Notice we have a domain of just 17. We're ready to substitute everything. Now, by properties of integrals, we know that this continuous function in terms of u has to be 0 because our definite integral is from 17 to 17. Let's do another example. Let's let u of x equal sine of x. Write your equation of differentials. And proceed to find u1 and u2. Ready to change this integral. We're going to change the way it looks, but yet it's going to have the same value. The new integral looks like a definite integral from -1 to 1, u to the 4th power du. And we can certainly integrate that. Now the emphasis here is this pattern. We have 1 subtract a -1, which will get you the quantity of 2. Now this 2 here is not a coincidence. There is something happening with algebra. So I'm going to introduce another idea. We're going to think of an alternative approach. And the reason why we could do this is because the domain values in the original definite integral are symmetric. In other words, you could see the domain as left pi over 2 units from the origin, and then right pi over 2 units from the origin. Alternatively, we are going to define a function here. We're going to call it f of x. And then we'll go ahead and observe f of the opposite of x. And in doing so, we're trying to figure out why that 2 appears. We know that the sine function is odd. And we know that the cosine function is even. This will yield this next expression. Which is just another name of f of x. This is actually the definition of an even function. What does that mean? That means we could actually double the quantity as long as we actually split the first integral in half. And how are we going to split this? We're going to split it like this. We're going to split it so that the domain is going from 0 to pi over 2. And then we put a doubling factor in front of that new definite integral. This leads us to these observations. The properties of definite integrals for even and odd functions with symmetric domain. So that is really key with these properties here. Notice the domain has to be symmetric. That means it has to be left a certain amount of units of the origin and then right a certain amount of units. If the function is even and you have a symmetric domain and you're trying to find a definite integral over the continuous function f of x, we know we could actually double the amount as long as you set your domain to go from 0 to a. Now for an odd function, if you recall your algebra and your graphing capabilities, you're going to realize if it was a continuous odd function and you're trying to find a definite integral with a symmetric domain, then that output should be 0. If you don't believe me, look at this example here, specifically example 11. Can you come up with an alternative way to express that this definite integral is going to ultimately become 0? Let's look at a few more examples. We already know cosine of theta is actually an even function. If you didn't know that, you could certainly prove it right away. Note, f of theta equals cosine of theta, and we could observe this. And from your trigonometry experience, cosine of the opposite of theta is simply cosine of theta, and cosine of theta is just another name for f of theta. Therefore, f of theta is even. That means we could actually do this. We could actually take the original integral, use symmetry, and split this in half, but double the quantity. Double this quantity here. Here's another function. First thing you want to do is actually verify that the continuous function that's given is actually odd. So we're going to define that function f of theta to be the third power of tangent of theta. We're going to observe f of the opposite of theta and see what happens. We know that the tangent function is odd, so that will yield this expression. Then we raise it to the third power. But this is just another name for the opposite of f of theta. Therefore, the function is odd. Finally, the definite integral must be what? The definite integral of an odd function on a symmetric domain will yield the finite number 0.